All right, we're going to learn today about momentum and impulse. So Newton discovered momentum well before he discovered all of his laws of motion we learned about inertia and all those things. And so momentum is just moving mass. So if I'm just sitting here in my chair, I have no momentum. As soon as I start moving, I have momentum. A truck can have a huge momentum, but if it's not moving, it has no momentum. So if you look over here, I have an elephant, right? And so the elephant is not moving. And since he's not moving, he still has no momentum. I don't care how big he is, because it's two things. It's m times v. So this p is momentum. So notice how it's in a box. Put it on your equation sheet. Let's add it to our units table. So let's make a little units table over here. We're going to add a couple. So we have momentum. Oh, I'm never going to be able to fit that word, but let's do my best. Momentum, which is a P. And then what the heck are the units? Well, let's see. Mass is kilograms and velocity is meters per second. So it's this really awful unit. It's a kilogram meter per second. That looks a lot like our Newton. Remember, our Newton was a kilogram meter per second squared. The only thing different is this is a second instead of a second squared. So you could also write it as a Newton second, because if I multiply this times seconds, that would give me kilogram meters per second. So we could also put, let's do it in a different color. So this would be or a Newton second, right? So we've got momentum, it's m times v. Then we have this thing called impulse. So impulse is change. Remember, change is a delta, so it's change in momentum. Impulse is the letter J, so J equals delta P. But P is just mv, right? See, P is just mv. But mass isn't changing, right? If my elephant starts moving, if I pushed him or something on a sled, I could change his velocity. But his mass isn't going to change. So really, momentum is m times delta v. So we're going to add impulse to here. So impulse. And it's a J, and notice it's the same units, right? It's still Newton seconds, so it's still kilograms meters per second or a Newton second, right? So it's the same thing as it was before. Now there's another equation for J. You might be kind of guessing when you see the newtons and the seconds. There's another equation for impulse, which we'll come to. So we've got two equations you should have added to your equation sheet. P equals mv and J equals delta P, which equals m delta v. So those should both be on your equation sheet, and momentum and impulse should be on your units table. All right, let's go to the next slide. So momentum is always the same. It's conserved. So just like Newton said that objects in motion stay in motion, and objects at rest stay at rest. Objects with no momentum stay with no momentum, and objects with momentum keep their momentum unless there's an outside net impulse change in momentum, right? But we've got to figure out what causes that. So I'll show in class my Newtonian device, because I can't do it while I'm doing these notes, but I will show you this. Some of you have seen this thing before, and so we're going to apply to that. So remember that momentum is always conserved. So that means that the mv before is always equal to the mv final. So keep that in mind as we watch that device and see how that works and how that applies to it. All right, so mv is equal to mv always, unless there's an outside impulse. Sounds very similar to Newton's inertia law. So in order to change the momentum, you have to change the velocity, which means you have to have a net force. And so again, it just sort of seems like Newton's laws, and it sort of is. But if you think about it, if I push something or pull something for a longer period of time, it's going to have a bigger change, right? So I can push my friend on their, so here they are on their sled, and here I am trying to push them in this direction across the ground. And if I do it if I push them with some force, I could just push them and let go, or I could push and hold and push and push and push and push. And so it would be for a longer extended time. And both those things are going to come into play to change the velocity. So therefore, J is also equal to Ft. So remember how I told you had to add another J equation? So J is also equal to Ft. But that means I could say Ft is equal to m delta V. Oh my goodness, there's all sorts of ways we can do this, right? So I could just do F times T. I can use this one in CK12. They do a lot of this where they're using this equation where they put the two together. So I want you to have all those equations on your equation sheet so that you can use them, and we'll use them in our sample problems as well. The units are still the same, Newton seconds, kilogram meters per second. We already have that on our units table, and it's the idea that force and time play a role. So that's why momentum's harder than force and acceleration, is because it's a change of a change, and there's two factors and two things are going on at the same time. Now I need you to keep in mind that there's a difference between force, so this is F net, and impulse, right? This is J. So impact force is how hard I pull, how hard I push, how hard I slap you. Right? It's a force. Ouch. Impulse is how much you changed the momentum. It is not how much it hurts. Think of this one as pain. If we want to kind of get to the concept, this is pain. This is change in momentum. I can't give you anything else. You imagine a truck barreling at you, right? It's going to have a lot of momentum. Now, it could hurt me. It could not hurt me. There's different ways I could get hit by that truck. So that has to do with how much force it gives to me. But the change in momentum is always going to be the change in momentum. So let's say I want to get a really small force. It's like I don't want to die from that truck hitting me. I don't want to get hurt when I get into a car accident. So I look at my impulse, right, for the same impulse, which is the change in momentum, right? So the concept is I've got a car and it's going 100 miles per hour, and then all of a sudden my car is going to stop. It's got the same mass. It's got a change in V of 100 miles per hour, negative, but it's still changing by 100 miles per hour. So my J, remember, is m delta V. So the car is going to stop. No matter what I do, the car is going to stop. But I don't want to die. So I want to have this F times T be the smallest force for the biggest, with the biggest amount of time. So people will always tell me, oh, an airbag, that's what we have here, an airbag, that makes the force less because it's squishy. No, that is not our physics terms, right? We're trying to learn physics terms. It's because you increase the time. So if F times T stays the same, the bigger I make that time, the smaller I can have the force. So by having a soft airbag, it takes me a lot longer to stop, and so it hurts a lot less. Falling on a wood floor. So this one you guys are not as familiar with, but if you've ever been ice skating versus roller skating in a rink, they have wood floors in the roller skating rink. When I fall on the wood, it has some give. The give increases my time, so it doesn't hurt as much. If you fall on ice, there is no give on a piece of ice. It's splat. It hurts. Jumping on a trampoline. What happens when you jump on the trampoline? Here I am, and it takes me time to stop, as opposed to jumping on the concrete, which would give me almost no time. So the bigger the time, the less the force. Now, this is for the same impulse, right? I'm stopping my car. I'm jumping out of a 2-story building. I don't know. Now, what if, on the other hand, I want the biggest force I can get, right? So remember, my J is equal to F times T. So now, if I have a small t, I can end up with a big force. So I have a little t and I have a big force. So I always like to look at a karate chop. You don't do a karate chop by just slowly pushing on the brick and hoping it breaks. You do it very quickly. For a car accident, you don't have a padded dash, so you just hit the window, no time at all. Falling on concrete, no give, very small amount of time. So these are all ways to increase the force. Now this one I'm not going to answer because we're going to look at this in class, but here's my question. What happens if you bounce? What would happen to the impulse? What would happen to the impact force? So remember the equation. M delta V equals F times T. If I bounce, and we're going to see it, so if I have an object, it comes in, it goes from V to 0, or it comes in, it bounces off, it goes from positive V to negative V. What's going to happen to my impulse? What's going to happen to my force? And we're going to see that in class.